It's a pleasure to be here and to talk a bit about deep learning and geometric algebra and our work we did. But I also have to be honest, I was bothering my head quite a lot how to talk to the elite of geometric algebra people and not like sounding completely silly. So I tried to relate that a bit to to what is in the media, what people usually do with when they think of deep learning, and what is actually also connected to my own research. So I will really start by going a bit into a technical explanation how things like ChatGPT work and what they are doing, how this translates to modern systems for weather, climate simulation or other large-scale simulations, and how things like geometric algebra come into play. It's a bit of a stretch, but it's really also what my daily life research was like the last couple of months, the last years. And there is a lot of like open places, open space for such ideas to come in. But there's also this tremendous paradigm of the more the better on the data and GPU acceleration side on the left. And I tried to bridge this gap a bit and try to tell. So I hope my introductions to these fields will not be too long, but also my whole life itself is a bit of a scatter field. So I started in physics and did my PhD in high energy physics. Then I switched somehow to deep learning and tried all this funky stuff. And then I ended up doing large scale simulations at Microsoft. So that is a bit like I've seen all these fields and that's hopefully enough to make these connections. And I think all this talk will be about these two different fields. The one is called geometric deep learning, and the other one is the transformer-based scale-up version, which we hear in the news very, very often nowadays. The paradigms are very, very different, and that's I think the main theme of my talk. On the left, we have this so-called Erlangen program, which is like a study of invariance framed in this beautiful city of Erlangen in the 1900s, and it was taken over to deep learning. And the idea is really to use this high-dimensional search space which arises if you build these networks with millions, billions, and now even trillions of parameters, and to make it basically better by telling the network how this data is aligned, which invariances are in the data, which conservation laws in the data, and so on and so forth. That training this network converges better, that the network finds better solution faster, and so on and so forth. So the real idea is to look at all the symmetries and scale principles in the data, find this data and use it. And that works extremely well for a lot of different problems. On the other hand, there is this, as I call it, transformer-based idea, where it's really completely the other way around. Whatever happens is in the data. You just have to build a network which scales, and you have to throw as much data as possible at this network, and the network will learn all these different symmetries, physics, whatever in the data. That is really the brute force approach, which works frustratingly well, I have to say, and we will see that all over the place. And it's like there is this huge deep learning is hitting a wall thing every month, and then there comes the next bigger and bigger model and is doing fantastically well. And I would have never thought that things like ChatGPT work that well, and that it can explain to me things like mathematically correct and so on and so forth. Of course, there are flaws, but these are the two different paradigms, and I think it's very, very important to understand the setting where one or the other is better, because obviously the geometric algebra work we are doing is in the left, and most of the work you read in the media is on the right. So just two very brief examples. What I mean by symmetries of the data, it's called this specific idea is called equivariant deep learning. It's actually very much rooted in Amsterdam. And the idea is really that basically the network reacts to to symmetries of the input. So you have this nice commutative diagram of some molecules, and what it tells here is that if you have this molecule, you put it into the network, and afterwards you rotate the output in a certain form. It should be exactly the same if you take the molecule, rotate it beforehand, and then put it through the network. So all this transformation of this input are reflected in the transformation of the output. That's of course very neat for the network, because then it doesn't matter which of these group elements basically is seen, because all of that is automatically presented in this group. That is a typical example of how to exploit symmetries in the input data for the network. On the right, we have an example of a large language model. So if I ask ChatGPT what is geometric algebra, the answer is, I would say, pretty decent. And yeah, and the thing is, this is like there's no symmetry, no conservation law, no whatever on the right. So I take my time to explain what is happening on the right, like a bit why this works and why this scales so well, because that's a thing which people usually don't know. They just think, okay, this is neural network, this is just compute, and so on and so forth. It took like people many years to figure out how to scale that stuff. And that's my first goal to understand, because if one understands how to scale, one understands probably how or one gets an idea how to get some really smart ideas into the scaling problems. However, I have to say I have not figured out that 100% myself, and neither do other people. So the first part of this talk is really I tried to make the connection from large language models to foundation models of science, because this is where I'm working from. So I will give a short introduction how a transformer is built. This is the fundamental principle of how to do language translation, and then I will show how we use that to do like large-scale weather modeling. And with that in mind, in the second part, we will really dive into how to use now geometric algebra, and then in the end, hopefully, you get an idea of how this stuff plays together. So there is like a few words which one usually reads, or which is often in the news, and I will try to walk through this a bit, but try to really focus on the most important concepts. The first concept is really important, is the so-called tokenization. So in language and in whatever you type into ChatGPT, you tokenize the inputs. That means you put it in some high-dimensional vector, and whatever word you type, whatever program you type, and so on and so forth, will be converted in the background into some vector. And for example, if you type in these two words, thinking machines, they are converted into vectors. In this case, for showcasing into with a vector with 4 entries, and so you can represent the input. That is called tokenization, and it's very efficient for language, because whatever language you're doing, whatever program you're typing, whatever math question you're asking the network, you can tokenize it. And then the second important aspect is positional encoding. So you need some information where in this sentence a word appears, and you need some information where the code appears, where certain things are basically placed. And the third and most crucial thing is the so-called multi-head self-attention, which is the fundamental building block for all these big models. So self-attention is basically the idea why the main breakthrough why that stuff scaled so well. And it's what it is doing is you have all these tokens, remember, and then the idea is that every of these tokens attends to other tokens. So basically, you need a mechanism how to tell each of the words or each of these tokens how they are related to all other tokens. And that is done with basically a very simple trick. You just embed everything with a simple matrix multiplication, like with 3 different matrices. These are will be later the learned parameters of our network. Then we get 3 different representations, and then we take this so-called the softmax function over that, and then we get an output. And what the softmax function is internally doing it relates each of the words to the other words. For example, it in this sentence is related to the animal didn't, and so on and so forth. And so this is really a new way when it was introduced in 2017, it was a very new way because it gave somehow the option to let the network have all connections a priori and to figure out which of these connections are the best. What people didn't know at the time, that it scaled so extremely well, and it's not fully understood why. But basically what happens, if you use this mechanism, you can really build it up tremendously, and that to a trillion parameters and to basically huge amount of data. The more you give, the better it gets. And most of this success, I mean, it's very simply put, but is due to this, let's say, architecture, or this agnostic architecture where it can find out whatever fits together the best. And this is really different compared to this geometric or algebra paradigm, and to the other different paradigms which I said in the beginning, because normally if you try to build a neural network, you first think of your data, how it is structured, and you can then try to use some sort of learning mechanism which fits on the data. For example, if you do computer vision, so if you try to work with images, you use something like a convolutional network, which is built around the principle that things which are close to each other should be treated together, and things which are far away from each other do not matter so much. And then you have this principle by sliding this filters over an image of so-called translation symmetry. So if you shift the image, basically the filter map should also shift accordingly. Another example is graph networks. So wherever you have a graph structure, like in network graphs or in population graphs or in molecules, atoms, and so on and so forth, you have some connections in between and some features attached to each of these atoms or people or whatever. So this is like in having a strong inductive bias. That's completely the opposite to what I showed before, where basically the only thing the network should see is how these things interact with each other. And it was not very clear that basically removing all this bias really helps, especially when scaling up. The next thing, and that's basically the final concept I throw at you, is the idea of pre-training and fine-tuning. Because if you read about ChatGPT and how much data is used there's no way that you get so much labeled data. You cannot do all these translations and all these tasks, there's no way that you just can find this data. So people were thinking of a smart way how to use data, and actually that this is called this unsupervised pre-training. So what you can do is you can use whatever sentence you like, and for example, mask out words, mask out half of the sentence, and then the network has to complete that. Because since you have the sentence already, you do not have to define a translation, you do not have to define a summary of the sentence, you just take the sentence, mask out some stuff, and let the network complete that stuff. And by doing this pre-training, you can use all the data you want, and basically the network already gets a very good understanding. And the more data you throw at it, the better the understanding gets. And then you can use this network, these huge monsters, and really fine-tune on some specific tasks. And I'm always thinking of if you show the network all the languages in the world without, for example, giving him the Korean language, it has seen so many different structures, so many different aspects, but all of this is quite related. And if you later just fine-tune it on the Korean language, chosen by me for no particular reason, you will see that it will do a very good job very fast, because it basically knows already what is going on. So that's the last thing, the pre-training and fine-tuning mechanism. And now, so basically I tried to explain how these big models work, and now we go into more the science part, because this is where it gets interesting, because there's where the math comes into play, and I will show you that you can play the same principle by using basically by using this transformers. So this is from one of the works we did, And that is like, if you look at weather and climate data, what you will encounter is that all of this data is very heterogeneous. So what I said about the different languages is also true for weather and climate data. You have different scenarios, so weather forecasting, local forecasting, daily forecasting, weekly forecasting, seasonal forecasting, climate projections, and so on and so forth. And all of this data is basically governed by some similar underlying principles, but is vastly different and vastly diverse. So we have physics at a different scale, which is very much related to languages. And that was one of the ideas, so I'm not going into too much detail, but in this paper, one can look it up if interested. It's really the idea to use all these heterogeneous data sets to basically see them as all the corpus of languages, to use all these data sets for pre-training, and then getting a model which has quite a good understanding of what weather and climate is doing, and then fine-tuning at any weather climate task you want without needing a lot of data. And that works extremely well, and was kind of, for me, the first time that I really went into this area of, I give up on the model, I only focus on the data. I try to get all this understanding of the data, and it's especially nice if you think of all these weather and climate simulations, because none of those are perfect. We all know that the climate scenarios we see, they usually are like between 3 and 2 degrees off, and we see that the weather forecasts are doing different things. But if we average out all of these errors, we somehow will meet in the middle, where basically a lot of true physics will be hidden. So the more data we acquire, the better the understanding of the world we'll get. And now the last thing you might ask, how is this related to transformers? And that's very easy, because you can look at an image as you can look at a sentence. So each part of the image is now a word, basically. And the only thing we have to tell where in the sentence is this part of the image. And that's like, again, positional encoding. So we need a clever way of telling the network where you're looking at. And then we can play the same game, and each of these different so-called patches interact with all the other patches, as we've done it in language. And it doesn't matter what the size of the image is, it doesn't matter how many channels it has, and so on and so forth. We can scale it up tremendously. And that is really the thinking which is going on. And that's just a very last example here. If you think of this big model which has seen everything, or which has seen a lot of data, and then let's say, okay, we want to do weather forecasting, so we keep everything fixed, so none of these parameters is changed. We only change the parameters at the very beginning and at the very end, and the beast in the middle we do not touch anymore. And then basically we can do like weather forecasting at some very decent level. And this is really the first way of looking at things. And the key takeaways are here. I tried to explain what is the difference between geometric deep learning and transformer-based deep learning, where the inductive bias in geometric deep learning is really all about symmetries and structure in the data, whereas the inductive bias in the transformer model is everything should see everything, and this is all about scaling and all about data. Whatever knowledge we want is in the data. And for large language models, the most important concepts are transformers, which are based on this concept of self-attention, so that everything interacts and scales, interacts in ways with all the objects. It's about the tokenization, how you use these different inputs to represent to the network. It's about the positional encoding, so where things stand between each other. And the most important concept is so-called self-attention and the pre-training. And you can do that not only for language, you can do that for all other data. That was, so to say, the prelude of my talk. And it's very important to really keep in mind that this is all about scaling, which is, like, for me, speaking as a former physicist, not very satisfying, right? I mean, we want to do something smart, but you cannot do something smart. You just have to throw data at it. And yeah, this is something one always has to have in mind, especially for me, switching from university to like large-scale compute. It's really true. They are right at some point, but it's still, I think, not the end of the story. And I also did, and that's the main part of the talk, really always had a favor on the geometric side of stuff, and I will basically now tell how, basically a bit randomly, I stumbled around this Clifford algebras, and I kind of used them to understand some of these questions of scaling in the PDE setting, so the large-scale partial differential equations. And after that, basically, I got into contact with Leo and Stephen, and basically they were telling us how it should really be done, and that will be the main part of this talk, where I talk about the paper on the right, this Geometric Clifford Algebra networks. So the most of this is done by this team. So the second paper is done by my intern, mostly David Ruhe. I have this fantastic collaborator, Jayesh, and my manager, Max, and Rian from Microsoft, and of course, Stephen, everyone knows. So it all started really that my job was basically to do large-scale simulation on partial differential equations, and I always had this hunch that using these large transformers or using these large models for this, it just felt a bit unnatural. And in my head, there was like weather data, there was this like pressure field, and there's wind, and there's always this connection. If the pressure changes, right, the wind starts to flow, and then the wind flows, which changes the pressure, and vice versa. So just very intuitively, there's a strong connection between pressure and wind field, but also, of course, between the x and y component of the wind field. So instead of using just these two fields and show the network them as three different channels, so pressure, wind x, wind y, there has to be something more natural to give to the network. And especially if you look at some of these equations which describe such systems, they're really coupled partial differential equations. So they literally say that these things belong together. So there's no way of showing these components to the network. And I was thinking, I don't need all this probably equivariant stuff and all this super nice symmetry stuff, because it might not scale that well. But I want to tell the network that this stuff just belongs together. And that probably can then be scaled very well. So that was a bit the insight, or the hope I had. And I have to give a very short interlude here, because to transport myself back a year ago, there was this so-called Fourier neural operators. That was the state-of-the-art method for solving such large-scale system. And they are basically doing a Fourier transform on the input, some pointers operation to the Fourier space, and then the transform back. Although, since it's neural networks, it's all high dimensional in the channel dimension, so you have a lot of these different maps where you do a Fourier transform on. But in the basic sense, it's really just Fourier transform, pointers, multiplication, and transforming back. Of course, like every deep learning paper, like with a lot of formulas and so on and so forth. But Fourier transform it was, and so I basically decided, okay, that stuff seems to scale very well. Maybe before like going to transformers, I tried to improve upon that. And I did a very simple example. I had this vector field, and I always had this vector field in my head, and this is like how it is done in deep learning. So for those who've ever programmed like in any of these tensor-based methods, you have some dimension which says how of these fields you have for one operation. Then you have the dimension of 2. This is really the channels. In that sense, that's the x component, the y component, and then you have just the nx, and so the number of points in x and y direction. So this is really seeing that the stuff has two different fields, the x component, the y component of the field. Yeah, and then I simply did what these models are doing. I did a Fourier transform, I did some random multiplication in Fourier space, because these are the weights of my network, and I transformed back. And of course, I destroy all the structure. Why should there be any structure left? But that is somehow completely against the, throw the structure into the problem into the network, and what you get out after your first pass is everything is destroyed. That was not what I wanted, because this is really exactly this X and Y component. The network should know a priori that they belong together without doing anything with that. And then I did something very simple. I just wrote it as one field, but with the complex numbers. So instead of writing an X and Y component, I really wrote it as a scalar complex number field. And then instead of doing two separate Fourier transforms on these two scalar fields, I did one Fourier transform on this complex scalar field. I again did some random multiplication in Fourier space and transformed back. And it seems much more related to the input now than it was before. I mean, of course, it's changed and so on and so forth, but that's how it should be, because we are manipulating it. We're trying to learn this manipulation. But it somehow seems that there's going on something in this with this complex transformation, which is more useful to see this internal structure. Yeah, and then one thing led to another. I looked at the internet about Fourier transforms and so on and so forth, and I stumbled across this work from computer vision 2005. At some point it gets a bit frustrating, because whatever we try to invent now was basically done in computer vision like 20 or 30 years ago. But they basically did that stuff, of course without deep learning, and of course without manipulating stuff. And it's not so much about what they did, but about the title, because then I learned about really that you can do very useful stuff with Clifford algebras, which I just remembered very vaguely from studying physics. So that was really the intuition. I won't go too much into this paper, because I really tried to put the focus on the next one. But nevertheless managed to replace operations in these large-scale networks, convolutions and Fourier transforms, and that really seemed to be beneficial. Maybe it's not the 100% correct way from a mathematical point of doing, but from a deep learning way, it definitely was beneficial, because it allowed to get rid of this separating everything by channels. So we now have everything as basically grouped as multi-vector, and we were able to define these operations and make the networks quite more efficient and quite working well at these large-scale PDE problems. And then we got into contact with Leo, Martin, and Steven. And there is especially this one paper from Martin and Steven, which were like an inspiration. And I also had a super smart intern at that time, David Ruhe, and we basically sat together and had some calls with Steven. What's how we go further? And then the idea was really okay, and now really use the power of GA to combined with the idea of this interaction to build these neural networks, because we already knew how to build neural networks, which now just really have to marry that with geometric algebra. And of course, I think I don't have to tell you the advantages of geometric algebra. For us, it was rather new, but I think we, especially with all these discussions I had with David, we learned rather quickly, at least to be able to have like some decent discussions. And I think the most important part for us as a deep learning people was that we could parameterize transformation of the space instead of transformation of objects. The problem is really that in deep learning everything is super huge. So you throw a lot of parameters at the problem, and not everything is like super mathematical elegant, and because a lot of things mix, so you have to somehow get a handle on that. And you remember the end goal, so to say, is to build a transformer out of that. So it has to scale, and that was the big problem we had, because just by building a very smart network with like 200 parameters, might be really nice, but then the next transformer guy says, come, I can do that with my transformer on my iPhone. So basically, we had to build something that scales. And there we had this idea, that's not a definition, but an idea of geometric templates. So it was really seen that we have these inputs, we have these geometric algebra objects, and they should always stay in the vector spaces. They should be manipulated, whatever, but they should stay in the vector spaces. It cannot be that the vector, like a multivector which only has vector components, suddenly gets bivector components and then trivector components and so on and so forth. It should always, after each layer, stay in each its respective vector space. And the way we transform these objects are via group actions. And that already brings us to this pin group, which is also the most fundamental group in the work of Martin and Stephen. So basically, I'm not so sure how often this was already mentioned. I just repeat very quickly. So that the key message is really that in whatever like dimension n you are, the composition of reflections in this space builds up the pin group, and that on the other hand also means that any element of this group can be written as a composition of reflections. And the most important part for us was that one has this group action via this conjugation rule, how you can act on pin elements or act on elements of the group. And that is what I meant by the inputs can only be transformed via group actions or linear combinations of such group actions. So we basically saw this pin group. We saw that we have this conjugation rule which exactly tells us on how to act on elements, that they stay in this group. We know that if we linearly combine such elements, we get another element of the group, and basically we have to build everything out of reflections. That was the idea we had, because then it's really clear that this will be the learnable parameters, because that's the only way of how to act on an element and to keep it in the group, so to say, to make it geometric compatible. And yeah, I mean, it sounds easier than it was, because, well, we had to get familiar with all these transformations. But as I said, it's all really built up from the pin group. So whatever operation you do, it's basically always, as explained by this great works, by composition of reflection. So it doesn't matter. So here for the pin group 301, it doesn't matter if you do translation, two reflection, parallel planes, rotation, reflections in intersecting planes, and so on and so forth. It's always composition of reflections. And then basically we had to come up with an idea of how to parameterize such reflections, and most importantly, how to get our data into this objects. And there it is really nice, and that was, I think, what took us the longest to understand, that how we can represent these objects in this way. But it was very helpful. We had these discussions, and basically we learned that objects are really the subspace which is left invariant. So a reflection leaves the plane invariant, a rotation leaves the line invariant. And that also means that since a reflection leaves the plane invariant, and we have this, we know how to convert the vector in a plane, and then vice versa. We basically can relate reflections and vectors. A bivector leaves and the line have this are related, and a line is left invariant by rotation. So basically we at that point knew how to present points by point reflections, lines by line reflections, and planes by plane reflections, and most of the time you have either points or vectors in your network. If you think of molecules, you either have the location of the molecule, which is the point, or like a velocity, and so on and so forth. So that was a lot of discussion. So we were like literally everyone in the office was hearing we were only talking about the sandwich product and about planes and bivectors, and they were like, what are you guys doing? I mean, but it was really, we tried to wrap our head how to represent the objects. For us, that was the hardest part. But in the end, we got this nice table. Also, I think thanks to Leo, he and David did some suggestion on the first draft of the paper. So there's really this connections between the group elements, the reflections, rotations, and whatever you do, in which algebra you do. The subspaces these elements live invariant, and the algebra it corresponds to. And of course, then you can play all the tricks, using different algebras, getting more powerful objects and networks and so on and so forth. So at that stage, we finally knew what we want to do. We want to use this conjugation to act on elements. We will parameterize this conjugation, and we also knew how to represent our objects in the neural network such that we can manipulate them. And then we came up with the principle of group action layer. So on the right, I have a standard vector matrix multiplication, which was always a bit which I always disliked when looking at this partial differential equations, because you have this, as I said, this natural interactions between vectors and scalar fields and so on and so forth. But now it was much clearer. Instead of having what is here the red, instead of having a vector of just 3 scalars, we now have a vector in each of these points. It's a multivector which represents the input. So if we, for example, have a 3-body problem, we of course would have 3 multivectors representing each of these bodies, and then we act on these bodies, but we are not. We act on these multivectors, but we're not doing that via standard vector matrix multiplication, but we're doing that via these so-called group action layers. And these group action layers, what they are doing, basically they use this conjugation, which really is the parameterized group action on each of these elements. So basically we would have this term we would have between that element and that element. So this would be an A and this would be an X. And of course the same for here and the same for here with different parameters. And then we mix them. That's why by linearly mixing them, and this is what basically makes it scale, because then you can have 3 inputs, and depending on how many of these layers you're using, you can have a different number of outputs. So we basically linear mix this transformation. And that was the key part to figure that out, because to get these like deep neural networks to work, you also have to make sure that the gradients you use for training, so basically the way you propagate the error through from the very end of the network to the very beginning of the network, gives you some learning signals, and that also means you have to have an understanding of how these gradients propagate through the layers, and that was really hard to get these gradients correctly, or the networks correctly initialized to exactly do that, that we can go bigger. But we figured out, and then the next thing in deep learning is you have a new idea, you want to do something, but you really have to prove also to yourself that it works. So actually, David and me, we spent like hours and days to think of a problem where this has a real advantage. I mean, we had a lot of stuff and we tried a lot of large-scale problems, but it was always, it never like 100% worked. And most of the time we worked with this, not say physically correct case, but it basically showed us in the simplest way what we want to do. So we had these objects which move out from the origin, and they rotate and translate randomly, but these translation rotations are sampled with respect to other objects. Why is this important? Because we have these rotations and translations of each object. So basically this is exactly where the geometric algebra comes in, because this is this pin group actions which you can learn. But you also have this these transformations are sampled with respect to other objects so that the objects have to talk to each other. And that's where our group action layers come into play, because then you really have to linearly combine the information of these objects. So that's how we basically designed this data set. And yeah, I always like, we have these nice graphs where we try different architectures. The most important one is this, and the blue is finally the GA network, and these are some other state-of-the-art networks. The problem, we had this blue curve always somewhere here. It was, as it is always, it's not really better than what you want to achieve. But then finally it clicked, and basically we realized that this whole transformation we were doing in the wrong order. So we had we were using the wrong algebra. We were just doing a rotation and then summing everything and then doing a translation afterwards. So it was part of, yeah, silly. But when we finally found the bug, it really worked out of the box. But it was a long way. So we first had to initialize everything. We first had to find out how to present that object and then how to combine these networks. But in the end, we really got it to work. There's one thing which is very crucial, is that the difference to these equivariant networks which I showed before. And that was also for us not clear, and we discussed that a long time, because a really big thing in deep learning, especially in molecular science, is that this molecule, they can transform. And as I tried to explain, whatever rotation you do, it should be visible on the output as well, and therefore you get a better representation here. But these networks work differently, because these equivariant models are global. So the frame of the reference is not affecting the trajectory. But our GCANs, how we call them, Geometric Clifford Algebra networks, they're not constrained. So basically they provide templates for these individual transformations. So in that, instead of transforming the whole object, we can learn the small transformation of each of these objects. And that's exactly why equivariant networks have a very hard time here, because they can only learn a nice representation with respect to the space, but they cannot really entangle these individual transformations, which are important here. And it's actually, when we finally had figured it out, in our heads, it's actually really important for practical purpose as well, because if you think of something like molecular docking, we have a huge molecule and some small molecule which is trying to dock to this molecule. It's actually this small molecule which is doing all these different movements and which you want to model, and not basically the whole space. And then finally, after we've finally figured it out, we really said, we did the litmus test saying, okay, now let's go to really huge problems. We were not going to transformers yet, because that comes with another set of problems. But we were going to very large so-called UNets, and it's, I think, the biggest geometric algebra network, or the biggest geometric deep learning network I've ever trained, with more than 200 million parameters. It's still not a lot compared to ChatGPT, but it's quite big. And we had this nice wind data set, the simulations with pressure and wind speed levels, and we were basically replacing convolutions in each of these networks with so-called geometric Clifford convolutions. So instead of basically sliding such filters across the image, we were now having again a point vector sitting in each of these points, and each of these operations are again this group action layers. The one thing we did, which is a deep learning trick, which is for sure not correct, and many mathematicians will now really please look away. But the thing is, we are in 2D space, and we have this coupling, which is there between pressure and velocities. So my idea is, I take that my responsibility is basically, we write that as a 3 vector. So basically we encode that as a 3-dimensional entity. And I mean, if geometric algebra people can use this this zero coordinate basically for basically to model things like homogeneous coordinates. We can also introduce another dimension and couple that. So that's we represented the data, and it worked out really well. I was extremely happy. What I'm really happy about is this curve especially, because again the light blue is our network, and on the x-axis one sees the number of trajectory. That for lower number of trajectories we are doing very well compared to all the other tuned networks is not surprisingly, but especially that for high number of trajectory, this gap even seems to get a bit larger. That's like extremely nice, because that means your model scales not only with parameters, because we have huge networks, but also the more data you give, the better it gets, and it like has huge advantage over the other networks. That was very reassuring. Again, we are not there yet. So basically, I'm quite sure that if we now go to very large scale weather problems and we go into the ring with the transformers, we will have a pretty hard time. But it's a very good and first step, and most of all, it gave me the confidence that we can really do that. So there is one thing which we have not figured out yet, and that's the speed. So our networks were quite fast compared to our first implementations, which were quite horrible, I have to say. But in principle, this GA from deep learning side should work quite well in the way that we have a lot of compute, a lot of dense operation on the GPU. So we don't need to shift the data all around and do some operation on the GPU and then put it back. A lot happens because this geometric product is a really dense operation. So everything what happens on the GPU basically should give a speed up, because everything is more denser. But that would require for us to write some customized GPU kernels, some CUDA kernels to do that, and none of us had the time or the skills to do that so far. Yeah, we will see how that goes, but that's definitely very interesting. I think that there is a huge potential there. And the next thing, which I'm also quite excited about, is so far we were always only talking about points, but especially if you think of larger objects like molecules, you have this certain group of objects. So this is a group. It's, I don't know, responsible that this molecule gets toxic, and this is another molecule group, and so on and so forth. And there's a nice way to basically represent these groups, and then this group can transform instead of doing that for each point individually. So that's definitely a way of how to extend that. And how this goes, it's not clear, but personally I see that there's a lot of potential there. And yeah, I mean, we try to open source whatever we can. So for those who are interested in this, how this climate modeling is working and how to do this large scale transformers, there's this Climax library. We've now open sourced the Clifford layer library. There's the code of David's experiments. It's not there yet, but it is just a matter of weeks, I think. And then we have also like how we do PDE modeling at scale library. So really trying to open source all that stuff. And these are my main co-workers, and of course you can reach out. And I think that's the end of my talk.
Thanks, Johannes. It was a really interesting talk. I had a question about, so I understand how you put the Clifford elements in and you can replace convolution layers with something that looks more sensible. What do you do with the sort of softmax ReLU type layers? Do you just get rid of them altogether?
So you mean the activation functions?
Yeah.
So basically, since we had this paradigm of just losing linear combinations of these transformations, we basically had to come up with a new activation function. But the equivariant literature has done a great job, because they also have this irreducible subspaces there, and basically in the activation function you for the higher order subspaces, you can only scale them, and we used basically the same tricks to come up with new activation functions.
Are they in the paper?
Yes, they're in the paper. Also normalization schemes and so on and so forth, you have to redo a bit, but yeah.
Anybody else?
Hi, very interesting, thank you. When you were talking about the sort of breakthrough that you had in going to complex variables, basically the Fourier transform is just a linear operation, so having two things it operates on, the real and imaginary parts, can't really make any difference in that sense. It must be the operations you're carrying out in the other domain that are different between the two cases. So can you say something about that?
Yeah, so first of all, this is not, that was my way of coming into that. So I had this intuition that as you said, if you do these two linear operations of like vector fields, and the whatever you do in the Fourier domain was kind of not like destroying the structure. And it just seemed that the treating that as complex number and doing one Fourier transform was much more robust against the transformation in the Fourier space. It was just more robust. And that basically got me thinking of how to, what to Google for, what I wanted to find. It's really this analogy that I had in mind. I tried to sketch basically this independence of channels versus this grouping of channels, which I tried to show with the weather. But it's as you said, you're completely right. It basically should be very similar, and of course you can parameterize the same way, but with random weights it really made a difference.
Okay, can I just ask one quick further question, which is about the scalability. It does seem really strange that you can take something that must be going at least like n squared in terms of relating each object to every other object, and yet somehow this works. Can you say any more about that?
Yes, I can. I should have. I have a very nice slide about that. So ChatGPT is now able to do like sequences of length of 32,000 tokens. So it means that each of these operations can operate on a length of 32,000 tokens, which is tremendously large, and that's why you can do all these translations. It's true that n squared is hurting, and that's why people since years try to come up with a better algorithm, which is just n or n log n, but there's nothing better. On the other hand, there is a lot of progress on hardware acceleration, how to better use the memory to make it like more efficient. I think if someone comes up with something that works the same and scales better, that's like that's $1 million idea, I would say. But yeah, that's the biggest disadvantage, but yet people come around that and the hardware gets better and better and it doesn't seem to hurt so much. Of course, if you do something like images, you have to come up with tricks because you run into this problem.
Thanks, that was a really good talk. So over the years, I've sat through many talks on Clifford valued neural networks. And maybe this is a question for Stephen as well. Now, I can't quite remember what they were doing, but they didn't work very well, basically. So is your big breakthrough actually the group operation, what you're doing in the layers? You know, because if you look at the literature, you'll find lots of stuff with people using Clifford valued networks. So have you got any feeling about that?
Yeah, so that's a very good question. I mean, I left out a lot of that part. Many of the insights come actually from my first paper, because basically what we did there is it's just some quaternion networks in one way or the other. Because quaternion, you can think of, scalar, you know what quaternions are. And then doing the basically this convolution, which is just the Hamiltonian or geometric product, is what people already did in the quaternion literature or whatever they called it. And I was in like a contact with many of these people. But what it turned out that if you do quaternion rotation instead of doing just the geometric product, was really working much better. And so this quaternion rotation is actually very much related already to the second work, where you do this really geometric transformation. because it's a sub field. And that was the unanswered question we had. We did not understand why it is not working better. And I really think that to make that work, you need a problem where it works. And that I think I first thought it's PDEs, but now I'm more convinced that it's in the molecule space, because that's really defined what are these objects, what are points, what are vectors, and so on and so forth. And you need really, you basically need to respect these geometric transformations. And yeah, I think that's a bit the difference, I would say.
Thanks.